হ্যালো। তো আমরা এখন অবধি আপলোড হতে থাকছে আই গেস। তো আমরা জানতাম ছোটবেলায় অ্যাটমের মধ্যে নিউক্লিয়াস আছে। নিউক্লিয়াসে কি কি আছে? প্রোটন আছে, নিউট্রন আছে, বাস। এরপর আমরা জেনেছি কি তার বাইরে অ্যাটমিক শেলস আছে। শেলসে কি ইলেকট্রনস আছে। এবার অ্যাটমিক শেলসকে আমরা এনার্জি লেভেলগুলোকে আবার আমরা ভাগ করে প্রিন্সিপাল কোয়ান্টাম নাম্বার, এজিমুথাল কোয়ান্টাম নাম্বার, ম্যাগনেটিক কোয়ান্টাম নাম্বার ভাগ করেছে। এটা ছিল মানে বাইরে অ্যাটমিক। এবার নিউক্লিয়াসের ভিতরে কি আছে আমরা কি কখনো এটা খুঁজতে চেষ্টা করেছি? আমাদের মানে 12th লেভেলে আমরা কি পেরেছি এটা খুঁজতে? তো আমার জানা মতো নিউট্রন প্রোটন এলিমেন্টারি পার্টিকেলস নয়। নিউট্রন প্রোটন is composed of other particles also. So আমরা এবার এটা জানার জন্য চলে যাই ধ্রুবজ্যোতির কাছে। ঠিক আছে, ধ্রুবজ্যোতি, রক্ষিত, ওভার টু ইউ।
Hello, my dear peeps. আমার নাম Dhrubajyoti Rakshit. I'm a physics undergraduate student. Now, today, on the auspicious occasion of 3-year completion of this beautiful YouTube channel, Juvenile Gurukul, which is founded by my very dear friend Debanujan Nath, I have been asked to deliver a lecture on the topic which is very dear to me, which is nothing but particle physics. As I have been informed that to celebrate the 3-year completion, this channel is going to conduct a lecture series for 2 days, that is today and tomorrow. So, I would request all of you to please stay tuned for more such videos to come. Now, let's move on to today's talk. I will be delivering a talk, or rather a discussion, on an overview of quarks and the standard model of particle physics. Now, up till class 12th, we all knew that an atom consists of 3 subatomic particles, namely the neutron, the proton, and the electron. But a thing about these 3 always stuck my mind. The mass of a neutron is of the order of 10 to the power minus 31 kilograms, whereas the mass of a neutron as well as a proton is of the order of 10 to the power minus 27 kilograms. I always used to think during my school days that why is it that an electron is so much lighter than the neutron and a proton, and why does the nucleus of an atom contributes to the majority, almost entirety of the atomic mass? We were to consider that the subatomic particles we learned up till the 12th standard, that is the neutron, the proton, and the electron. All of these are elementary in nature. Now, what does elementary in nature mean? Elementary in nature means that those particles can never be broken down into smaller particles. Now, an electron's mass is so less. It's of the order of 10 to the power minus 31. So, I could still consider that an electron is an elementary particle. But should I consider a neutron or a proton whose mass is much higher than that of an electron as an elementary particle? Now, this is where higher level physics kicks in. As we go into the realm of high energy physics, we come to know that neutrons and protons are indeed composite particles. That is, they are made up of more elementary particles. Now, what are these elementary particles that comprise the neutron and the proton? We would learn further on. Now, let's start from the very basics. We all have learned that in the universe there are four fundamental forces. These four forces are the strong interaction, the weak interaction, the electromagnetic force, and the gravitational force. The gravitational force being the weakest of all these forces. Now, why am I stating about these four forces while explaining the realm of particle physics? Well, particle physics is quite different to that of classical physics. The very idea of an atom containing three subatomic particles is very classical in a way. But in particle physics, we come across a lot of more particles other than these three. So, we have to shrink our domain. Our domain should be inside the nucleus, inside a particle, where the strong nuclear force or the strong interaction prevails over any other forces. Any other forces. So, it was just to mention that particle physics deals with the strong interaction. The strong interaction has an integral part, an integral significance in the particle physics realm. Now, as we dive in the topic, which is quite visible, I hope so, in the PowerPoint presentation, we must learn about the history of particle physics. I believe that learning about the history of something that has grown up to a large level will surely give us the fundamental values and help us correlate with all the notions of that topic. Therefore, let me start the presentation. As you can see on the screen, I've written a heading, I've typed a heading, sorry, History of Particle Physics. Now I've written, I've typed the same thing I stated a few seconds ago. That before learning the topic, we should learn about the history of the topic. In fact, history of science is becoming quite popular these days. Now, while studying about the history of particle physics, we of course don't need to memorize a lot of dates and names of dead physicists. Of course not. But we just need to get familiar with different particles that were discovered over the years and how they really do fit in the picture of this field. Now, if you would ask me that who is the pioneer of particle physics, I would rather say that the great British physicist Paul Dirac, who unified the two fundamental forces at that time, that is the quantum mechanics and the STR or the special theory of relativity, and gave us the concept of relativistic quantum mechanics, is the pioneer of modern particle physics. But many would disagree with me, and they have a valid point, because the very start of particle physics actually begun in 1897 when Mr. J. J. Thomson discovered the electron while performing an experiment using cathode ray tube. The discovery of electron motivated a lot of people, which led to developments continuing over the 20th century, with a lot of scientists and their groups performing experiments to find out more about the atom. Dr. Ernest Rutherford and his group were able to discover the nucleus of an atom using the alpha particle gold foil scattering experiment. They also found that almost the entirety of an atom is empty, with the nucleus, which was bouncing back the alpha particle, the positively charged alpha particle, sourced from a polonium source. The positively charged alpha particle went through the atom, and only a few of those alpha particles were deflected. Extensive studies showed that the alpha particles which were deflected due to the positively charged nucleus, due to the positively charged entity, which is now known as the nucleus. And a few of those alpha particles totally bounced back, following the same path they traversed. This proved that the entity inside an atom is positively charged. Now, the term proton was coined by none other than Rutherford in 1920. As it was believed that the nucleus of an atom is composed of a proton and a neutron. I mean, protons and neutrons. Now, as the mass number of an atom increases, the number of protons and the number of neutrons will also increase gradually. That is a different topic. Now, by the 1930s, a few of the elementary particles which were known were the electron, the proton, the neutron. And surprisingly, the very famous neutrino, which is also known as the ghost particle. Now, the God particle is the Higgs boson. The ghost particle is the neutrino because it's neutral. We will discuss about neutrino in some other video. Now, another particle which was known by that time was the photon. The positron and the neutron were discovered by Carl Anderson and James Chadwick, respectively, in the year 1932. Now let's move on to the next slide. Here, I have presented a chronology of events related to the discovery of different particles important in the field of particle physics over the years. Now, as you can see on the slide, we have also mentioned before that in 1932, the positron was discovered by Carl Anderson. We have also mentioned the same thing here. And the neutron was discovered by James Chadwick. Now let's move on to the next slide. Yeah, I mentioned about the neutrino in one of the previous slides. Yeah. So present day, we know that there are two types of beta decay. One of them is the positive beta decay and another is the negative beta decay. Now, the positive beta decay gives out a neutrino, but a negative beta decay gives out an antineutrino. What is an antineutrino? Antineutrino is the antiparticle form of the neutrino. We will discuss about antiparticle in this video only. Stay tuned. Now, in 1933, Enrico Fermi, the famous physicist, discovered beta decay. But what he discovered was the negative beta decay due to weak interactions. The equation which is followed in the negative beta decay is visible on the screen. This equation. Here, N stands for the neutron, P stands for proton, this is electron, and this is the antineutrino. So this is the negative beta decay reaction. Now, in 1935, Hideki Yukawa presented his meson hypothesis. He said that the nuclear force, that is the strong interaction, was due to the exchange of particles with mass, which he termed as mesons. We would learn about mesons in this video. Now let's move on to the next slide. As we go over the years, in 1937, mu lepton or muon was discovered by Carl Anderson and Seth Nethermeyer. Now, lepton, this is a new word. I would discuss about it in the coming slides. But for just a general introduction, no, rather I would discuss it in the coming slides. That would be okay. Oh, but for an introduction, I'm just mentioning what is a lepton. So leptons are nothing but constituent particles which are mentioned in the standard model. These leptons include electron, muon, and many others. So this muon, which is also known as a mu lepton, was discovered by Carl Anderson and Seth Nethermeyer. Now let's fast forward to 1946. We have the charged pi meson. Meson we will discuss in the coming slides. The charged pi meson or the pion was discovered by Cecil Powell. Now, this is another particle which is found in particle physics, which is relevant in particle physics and was founded in and was discovered in 1946. Now, you can see I've put a snap of an equation pi plus to mu plus and nu mu. So let me explain this equation. Now, pi plus is the charged pi meson, which is mentioned, which was discovered by Cecil Powell. Mu plus is the positively charged muon, a muon which was discovered in 1937. And nu mu is the muon neutrino. We would learn about types of neutrinos when we would study the standard model. Now, let me write it for you. Okay, so uh, this is the, I'm sorry, this is the pion. Erase it. That's creating a problem. This is the positively charged muon. So this is muon and this is positively charged. And this is the muon neutrino. Okay. Now, in 1950, the the neutral pion was discovered. Now, in 1946, the pion which was discovered was a charged entity, and in 1950, a neutral pion was discovered. So, pi naught, this implies a neutral pion. We will discuss about pion when we will have an overview of the standard model. And this and this is gamma, both of them, which describes the gamma photon. So this is very similar to QED or quantum electrodynamics, which we will learn in the next slide. Now, quantum theory of electromagnetism or the quantum electrodynamics, better known as QED, which was pioneered by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, states that charged particles interact via exchange of photons. So, it means that when a charged particle, for example, now for this example, I need to mention what an antiparticle is. So, what is an antiparticle? We have studied that the antiparticle of electron is a positron. So, what is a positron? Positron and electron both have the same masses. The difference is between their charges and their magnetic moments. Electron and positron just have the opposite charges. This is a classic example of a particle and an antiparticle pair. Now, to understand the quantum electrodynamics, let us assume that an electron is coming towards a positron, coming towards a positron. Now, they both are oppositely charged, so obviously they wouldn't repel. So, an electron hits, my bad, I'm sorry, I need to erase it. Thank you for your patience. Now, an electron charges towards a positron. So, this is the particle denoted by P, and this is the antiparticle denoted by NTP, or vice versa. Like the antiparticle of a positron is an electron. So, what will happen? It would cause annihilation. Both the particles will annihilate and create a burst of energy, which is nothing but photon. It is photon. So, as you can see, uh, this is a charged particle. This is also a charged particle. Charged and charged particle. So, both of these charged particles interacted with each other and photon was released. This is an example of quantum electrodynamics or quantum theory of electromagnetism. And this was pioneered by these three scientists, which you can see on the screen. Now let's move on to the next slide. Oh, yeah. So this equation you can see neutral pion gamma plus gamma is somehow similar to the theory of quantum electrodynamics, as the vice versa can also occur. Right. So let's move on to the next slide. Okay. So no, I'm sorry. Now, in 1947, a new type of particle known as the kaon or the K meson was discovered. It was discovered by Clifford Butler and George Rochester. They termed this particle a strange, long-lived particle discovered in the cosmic ray events. The discovery of kaon gave rise to a new quantum number, strangeness. This quantum number is the fifth quantum number, the other four being the principal quantum number, the azimuthal quantum number, the magnetic quantum number, and the spin quantum number. Oh, now, it was discovered at Brookhaven, New York in 1952-53. Now let's move on. In 1955, antiproton was discovered by Owen Chamberlain and Emilio Segre. We learned about the positron and the electron. So the positron is the antiparticle of an electron. Just like that, antiproton is the antiparticle of a proton. When a proton will hit an antiproton, similarly, annihilation will take place. Now, the 1960s. and the 1970s were nothing but a golden period in the field and the study of particle physics. This period was known as the particle zoo period. Even Dr. Oppenheimer, who was the pioneer of the Manhattan Project, described the ongoing development of particle physics in the 50s as a subatomic zoo, as the diversity of particles being discovered was nothing short of a zoo. Hundreds of elementary particles discovered, rho, omega, and many more. This diagram shows a chronology of events, chronology of discovery of different particles over the years. Now, all these particles are explained as combinations of more fundamental particles, which are known as the quarks and the antiparticles. We would extensively discuss about quarks in this video. 1964. The year was 1964. The particle omega minus was discovered. A new quark theory was introduced by Murray Gell-Mann and George Zweig, who predicted a yet unseen particle, this omega minus, which had three strange quarks. We would discuss about the types of quarks and everything in this video. This theory was widely accepted, and this theory was very much victorious. Now, fast forward to the 1970s. The 1970s was the era of quantum chromodynamics. Quantum chromodynamics stated that quarks interact via the exchange of gluons. We will discuss about gluons, but just for introduction purpose, gluons can be considered as particles which glue the nucleus together, which glue the particles, the neutrons and the protons together, which glue the quarks together. We will discuss about the quarks later on. During this time, a new theory came up which described the weak interaction between the particles combined with electromagnetism. And this theory is known as the electroweak theory. It predicts omega plus, omega minus, and Z0 as the carriers of weak force. Now, these are new particles which came up as a result, as a consequence of the particle zoo. In 1974, a new quark known as a charm quark was discovered at Stanford and Brookhaven, USA. Up till 1970s, it was known that there are three types of quark: the up, the down, and the strange quark. But a new type of quark Charm quark was discovered in 1974. I'm repeating it again. The concept of quark will be explained in this video. All these things will be explained. Now, in 1975, the third charged lepton, tau, it is a charged particle, remember? So, it's denoted as tau minus, proving its charge is -1, was discovered at Stanford, USA. In 1978, the fifth quark, known as a bottom quark, B, was discovered at Fermilab, USA. In 1979, gluons, which hold together a particle such as the neutron and the proton, was discovered in 1979 only. In 1983, the carriers of electroweak interaction, omega plus, omega minus, and Z naught, were discovered at CERN, Geneva. In the 1990s, the number of neutrinos, the ghost particle, was limited to 3, as referenced by the measurements of the Large Electron Positron Collider at CERN. It is still one of the biggest particle accelerators ever created by mankind. Ever created. It comes only after the LHC, which is an engineering marvel. A total of 6 quarks were implied by this time. Now, in 1995, the sixth quark, top, was discovered at Fermilab, US. Possible evidence of the Higgs particle was given by the Large Electron Positron Collider, LEP, CERN, but was not confirmed in the 2000s. Now, as you can see on the screen, this is a summary of all the chronological dates that have been mentioned in the slides. From 1947, when a kaon was discovered to have a mass several times that of a pion. It was discovered that it is unstable and about 970 times heavier than an electron, to the discovery of the antiproton. 2. The concept of particle zoo. 2. The discovery of the charm quark, to the discovery of quantum chromodynamics. All these discoveries were stepping stones for something big. Now, I have mentioned that in 1974, John Iliopoulos presented the first version of the standard model. What is a standard model? Now, in chemistry, we have a periodic table. The periodic table is a guide, is a is rather a, what should I say, is rather a database, I would say, of all the known elements found on the earth, both naturally occurring and laboratory prepared. Just like that, the standard model is the database for all the known particles which are present in the microscopic world. Such a chart was given by John Iliopoulos in 1974. Over the years, the standard model of particle physics has developed, has improved immensely, and experimentation is on its peak, where people are working day and night to discover new particles to answer humanity's biggest questions. Now, the year 2012, which is probably one of the biggest years, embarking millennial achievement in the field of particle physics. Yes, I'm talking about the discovery of Higgs boson. Many of you must have been familiar with this discovery. It's still one of the highly talked topics in the realm of particle physics. Now, Higgs boson was discovered at Large Hadron Collider, Geneva. It's present on the border of France and Switzerland. Now, Higgs boson is a type of boson particle. Now, what is a boson particle? We would discuss more about the boson particle when we look at the standard model, which is up in the coming slides. But I would like to mention that why is it named boson? There was a famous Indian physicist who greatly contributed in the development of particle physics and modern physics. The name of that scientist is Satyendranath Bose. The great Paul Dirac coined the term boson to commemorate the contribution of S.N. Bose in the field of particle physics and modern physics. Now, it's named Higgs after Mr. Peter Higgs, a Nobel Prize winner, due to the discovery of Higgs boson, due to the concept of Higgs boson, which was given by him and his team in way back in 1964. Where he introduced the Higgs mechanism and gave us an idea of a field known as the Higgs field, which is credited to impart mass to particles which interact with it. Higgs boson doesn't impart mass to particles. It is the Higgs field which imparts mass to particles. And Higgs boson is simply a wave in that field. Any particle can be represented by a wave in its own field. Higher physics, high energy physics, states that particles do have their own fields. For example, an electron is a wave in the electron field. The discovery of Higgs boson in 2012 was indeed one of the legendary moments in the history of particle physics.